In laminar pipe flow, the velocity profile is parabolic. Near the walls, there is a considerable quantity of relatively slowly moving fluid. Dye, injected near the wall, marks some slowly moving fluid. When it leaves the pipe, it falls with a steep trajectory. Notice that the slowly moving fluid near the top of the pipe also falls steeply. The rapidly moving fluid from the middle of the tube falls with a flat trajectory. Compared with laminar flow, in turbulent flow, the mixing of momentum causes the velocity to be much more nearly uniform. The fastest fluid is not quite so fast, and there is very little slowly moving fluid. What little there is can be dragged along with the rest when it leaves the pipe. Nevertheless, the velocity must vanish at the wall, so we can regard the wall as a sink for momentum. Turbulence increases the rate at which momentum is transferred toward the wall. Thus, with turbulence, we need a larger pressure gradient to replace the momentum lost to the wall. Although the principal motion of these bubble patches is downstream, there is a very appreciable cross-stream component. Fluid moving across the stream in this way tends to carry its properties with it. It is these cross-stream velocities which do the mixing. For example, the momentum close to the wall is appreciably less than that in the center of the stream. The cross-stream motion carries low momentum fluid into the center of the stream and high momentum fluid toward the wall. Thus, the turbulence transports momentum. In this shot of the Fraser River at Hell's Gate, we can see great volumes of slow-moving fluid which come up from near the bottom and very much reduce the average speed of the surface flow. Turbulence can transport more than momentum. With scalars, such as dye and heat, mixing may be primarily a matter of stirring a fluid which is already grossly homogeneous. On the other hand, if we have a mean property gradient, the most important effect of the mixing may be a transport of some property, as dye is transported across this channel. The wall here has been deliberately roughened in order to increase the ratio of turbulent to mean flow speeds. The dye also helps us examine the velocity field. The blue dye is injected at the center of the channel where the flow is fastest. The red dye is injected near the wall into the slowly moving fluid. Notice how, even at the same distance from the wall, the filaments of blue dye move more rapidly than do the red dye filaments. The forward momentum of fluid moving towards the wall is on the average greater than that of fluid moving away from the wall. The region near the wall, then, continuously gains momentum at the expense of the region near the center of the flow. Since rate of change of momentum is force, and force per unit area is stress, we see that the presence of the turbulence produces a stress, the Reynolds stress, within the fluid. The Reynolds stress is additional to the ordinary viscous shearing stress and produces the increase in drag, which we found in our pipe flow when it became turbulent. Now, let's have a closer look at the mixing of a scalar. In this vessel, we have two miscible liquids, one floating on top of the other. If we leave them for a week or so, molecular diffusion will do a fair job of mixing them. Much more thorough mixing can be accomplished in less than a minute if we make the fluid turbulent. In this case, too, the end result is intimate mingling on a molecular scale, although the turbulent motions themselves are not much smaller than about a millimeter. The role of the turbulence is to make the inhomogeneities more vulnerable to the effects of molecular diffusion. Perhaps this can be clarified by animation. Let us suppose we have a blob of something which we plan to mix into the surrounding fluid. If the fluid is turbulent, the irregular motion will result in a strain, which will pull out the blob into a greatly elongated form like this. In turbulence, there is a great range of different scales of motion. At the same time as the blob is being pulled out, smaller scales are distorting it. And smaller scales still produce an even finer grain structure. Eventually, the interfacial area becomes so large and the property gradient so steep that molecular diffusion is able to act quickly and produce efficient mixing. In reality, of course, all the events we saw sequentially occur simultaneously. One of the curious properties of turbulence is the fact that although the Reynolds number is very important in determining whether or not a particular flow will be turbulent, once it is turbulent, the value of the Reynolds number is of very little importance as far as the large-scale motion is concerned. These two jets look pretty much the same. On the large scale, a turbulent jet is a turbulent jet, period. However, if we turn our attention to the small-scale motions, as seen in these shadow graphs, the effect of the Reynolds number is pretty clear. Notice how much finer grained is the structure in the higher Reynolds number jet. The reason for this can be understood if we consider the energy dissipated. In these two jets, the Reynolds number difference is produced by having different viscosities. All other conditions are the same, including the energy input into the jet. Therefore, the two jets dissipate energy at the same rate. Now, energy dissipation in a Newtonian fluid is given by the viscosity multiplied by the mean square of the strain rate. Dimensionally, viscosity multiplied by the speed squared divided by some characteristic length squared. This can be written. In the two jets, we have the same energy dissipation and the same characteristic speed, but have different viscosities. Therefore, the length scales must also differ. The high Reynolds number jet with low viscosity must correspondingly have a smaller characteristic length scale. This leads us to one of the most important concepts in the study of turbulence, the idea of the energy cascade. As we have seen, under certain circumstances, a large-scale motion can become turbulent. Some of the energy in the large-scale motion is converted into turbulent energy. The largest scales of the turbulence are usually smaller than, although comparable with, the scale of the basic mean flow. However, usually these large-scale motions are themselves unstable and break into smaller-scale motions which take energy from them. Finally, the energy passes down to scales, like those revealed by this shadow graph, which are so small that the Reynolds number is too low for instability. The energy is dissipated by the action of viscosity. The analogy with a cascade of water is a useful one. Here, the only property of the flow at the top, which matters at the bottom, is the rate at which water passes down the cascade. Similarly, in the turbulent energy cascade, at the smaller scales of motion, it is only the rate of energy dissipation which is of any consequence. This rate, together with the viscosity, determines the size of the smaller scales of motion. At high enough Reynolds number, the small-scale turbulence loses all directional orientation. It becomes isotropic. Figuratively, it doesn't know which way is up.